Alright, time for another DraftPhysics.com. DebatePhysics.com also. But again, debate requires that you make an argument and then somebody counters the argument, explains how the argument needs correcting, or it's just a little bit imprecise, or you said something a little bit wrong, something like that. And instead, no, we don't get any of that. No concession to any of the stipulations, axioms, foundational facts surrounding particularly these individual experiments. So you can go back to the Deschardelet experiment, denting clay with round objects, and the fact is there wasn't an argument then that was intelligent enough to dissect the truth, which was that experiment doesn't show shit. So anyway, and in this case, we're talking about levers and catapults and trebuchets. And again, people just don't want to argue the facts. They don't want to get established this foundational understanding of how the thing works, and instead just do this buffooning. And so I haven't played this video, but again, it's just, Ian Gosling pretending I didn't make the last 3 videos I made. So, so let's move on. I'll play it later in the video, perhaps, see how far we get. So I'm going to go over all the crap that he's ignoring, that, might argue that these are now established facts. We've learned something in doing these experiments, and unfortunately, the first principle, I guess the first thing that needs to be conceded, is that we don't live in the idealization. So, these experiments aren't going to follow an idealized, there's no gravity, and there's no this, and there's no that. No, we're not in that world. So there is all of these subtle but substantial problems. So the first argument is you can do these experiments. So we'll do the lever first, the simplest. And the idea would be is, you're going to put something in and get something out. And, the simple argument is there'll be a speed of movement here, in this location where it's going to land, and that you can create a movement over here that'll be twice as much, twice the velocity. And theoretically, you could put half the mass here and a full mass, drop it here, and transfer the energy. But the theory only works if this isn't a problem, the weight of the lever itself, the mass of the lever. So no matter whether you're in gravity or you have it horizontally, the problem is it does take energy to initiate a movement. So if let's say if I hit a lever, I put energy in and it'll keep oscillating. Well, I have to put energy in, and that oscillation is just showing me how much energy it took to move the lever itself, all by itself. So you're going to lose that much energy. You can't avoid it. So there's going to be some loss in the amount of force that this actually hits with. It's going to be force minus that gets to this other side. Okay, you're going to have lost a little bit of force because you're moving this physical mass. And so that's why it's important, that the experiment comes out differently depending on how heavy the lever is, how much weight it has compared to the objects you're going to try to move. So that would be one of the arguments that has been made, is that it does matter. The weight of the lever, the lighter it is, the less relevant it'll be. The heavier it is, the more it will change the experiment. So the argument is that you have force minus going over here. So for any action that's happening here, we know we're not going to get the pure, what we expect over here in terms of a force. It's going to be weaker, which means you have to make adjustments to the position to find the position where you can maximize this motion, get the most out of it, without it not matching this deceleration. This deceleration isn't going to be the actual deceleration of the object. It's going to be the deceleration, okay, with this inertia of the lever subtracted. So you have to move this in a little bit, and you'll get less velocity. It won't move as much, but it will move consistent with this movement, which is the important part, and therefore you'll get your 90%, let's say, and 10% lost to the lever. But you have to make these adjustments. You don't make the adjustments, then this is essentially heavier than the 2 mass. You don't have it's not a 1 to 2 relationship in terms of the energy anymore, because you've lost some of it here. So you have to make the object a little lighter to compensate for the fact that the force is a little weaker. All right, so that's explaining the initial experiment. Now, the truth is, I thought, hey, you know what, let's try to get rid of that problem, okay, by making the lever less relevant. And so I thought a catapult would be a better idea. And unfortunately, I was wrong to think so. Yeah, because it has its liabilities. And again, the liability is essentially the weight of the lever. Now, in this case, we don't have to worry about a precise deceleration, and we don't have to worry about the lever being balanced or any of that, because what's going to happen on one side is always going to be the same. It's a spring. It's going to create the same force every single time. And the idea is that you're going to use the idealization of thinking that, okay, pushing a 2 mass at one distance is going to be the same amount of force as it's going to take for a 1 mass at 2 distances. And that idealization, again, is completely dependent on the notion that you can have an irrelevant massed lever. And that's tricky, because if you make it light and thin, it bends a lot, and that's a liability. But if it's rigid and heavy and weighs a lot, then you get the problem that Ian had in his video, where 1/3 of this total weight of this object plus the lever, and then for this object plus the weight of the lever is only 1/5. And so now you have a big problem in the sense that you're moving more lever over here because of the difference in how the lever's interpreting the total mass of the lever. It's moving plus the mass of the object, because that's all in the catapult case you're doing. You're just moving a mass. It didn't matter whether I put the 2 mass here or here or here or here. It'll still move with a substantial amount of velocity, because unlike the other circumstance where you're dropping an object in, you don't have to worry about the object you're dropping reflecting, or the object you're dropping going right through and still having its energy. In this case, the energy is always the same going in. So it's either going to move the object or it's going to move the lever. And the fact is, the lever has the interesting property that the further out you put the object, the less work the lever does, and the more energy goes into the object. Just happens to be the truth. And so it has its, what you could argue to be its maximum limitations. You won't forever gain that advantage. But what's really happening in this experiment is, yeah, you're really just measuring the force on the spring minus how much the lever moves. And so you're really just comparing 2 objects by putting them on the spring and launching them, because that's all the spring sees. It just sees that if the 2 masses on the lever, this is all it sees. It just sees the whole lever plus a 2 mass. It just sees a weight, the total weight. And the weight doesn't change if I put the 2 somewhere else. It doesn't change the fact that it's just mass. And it's going to move that total amount of mass. And, it's sort of that simple. So I pointed this out, and the way to get around it okay, is to recognize the problem exists, that this 1/3, 1/5 thing exists. And the only way you can fix it is you have to try to make these two numbers equal each other. So you either have to move the two mass in and make the lever work harder to use up more of a percentage of the momentum. So if I move the two object in, then I can get the lever to take more of the energy until it's 1/3 of the energy. Or I can move this out further, okay, which will mean the lever does less work. That means even though it's 1/3 of the mass, okay, the lever will be 1/3 of the mass. It'll only be consuming, because it's going to move less to create more motion the further out I go. It does less work. The total lever moves less to create more action the further out you go. So I can get it to consume less if I move the lighter object out further. So it will go faster and faster and faster as I move it out, until I get this 1/3 to match this 1/5. So obviously there's a pretty good difference there. So 2/5. So you're going to have to do some work, okay, to get it to match. So this I've had pointed out. I could just say, okay, if you're not going to respond to this point, I mean, it's a critical point, understanding that the lever is taking a percentage of the energy and the percentages aren't the same, which is totally against the idealization. The idealization is assuming the lever's consuming the same amount of energy for both instances, and it's clearly not. Okay, so so you do have to make the adjustment. Now, if you can't argue that or point out how that's not true or something like that, then we're just stuck with me understanding that that's the truth, that you have to recognize that the mass doesn't change. I can put the mass out further and further. I really don't make it weigh more. It physically is still only a half mass object or a 5-ounce object, and you're pushing it, and that's it. And that's what the spring sees. All right, it's real mass. But the fact is that it's going to change because it's going to move that real mass a higher velocity, and it's going to do it by moving less. It's just the truth. Further out I put it, the less work the lever actually does. Alright, so I made that point, and that was to be a critical point in arguing that, well, what you're going to find is that you really do have to make this adjustment. If you don't make it, alright, it's really not a fair contest, because 1/3 of the total force is being consumed by the lever here, and only 1/5 of the total force is being consumed by the lever here. Alright, no, I think that went well enough. The drawings are not, I really don't know how to move these cameras, but I do have to move the camera. Yeah, it's got a parallax problem, so gotta work on that. Alright, should be better. So let's go over some of the previous experiments and just point out how what can be gained from recognizing the existence of these other experiments and their results. Now, I did my own, okay, with a lever that was a hollow tube. All right, and I didn't weigh it, okay, but I was using steel bars, okay, that were quite heavy. All right, and the fact is that I didn't get twice, but I got a lot more than, okay, 1.4 the velocity, or you could argue 1.5 the distance. So maybe I got 3/4 the distance. And you sort of can use distance. I mean, it is on an arc, but the arc is really just saying the distance is just the velocity. So the fact is that half that arc distance is going to be twice the velocity, something that swings this whole distance in the same time that something else swings this. And I noticed that in my experiment, that they left and the light one went twice as far, more than twice as far, let's argue, because it has to really be more than twice, because twice the distance is twice the velocity, so it was like twice the distance. But that's the height is 4 times the height, so that's the part that gets confusing. So you're comparing height and distance. Distance is 2 to 1, height is 4 to 1. Okay. So you can see some of it visually, especially with a pendulum that had 88 inches, to the object. It was a very long pendulum, so it was very flat at the bottom. All right. And so yeah, this is before I figured out that the lever still consumes energy, and that you have to account for that. So I didn't put it further out. So I had it at the wrong location, in the sense the lever was consuming more of the energy than this lever's motion. This motion was using more of this thing's energy, okay, because the total mass difference. All right, anyway, so that was one experiment. That's an indication. So yes, I didn't get the perfect answer, but I got certainly more than the 1.4 or the half the distance argument. Half the distance means this goes this way and this goes 1.5 that distance, so it goes this far. Not that it goes twice the distance. Mine went almost twice, so it was close to a lot more than 1.4. All right, then anyway, so then we have the Brozo experiment, which is worth highlighting again. And yes, there were disadvantages. Now, his lever, I would speculate, had to be much lighter than the objects he was launching, because he got fairly consistent results. Now, the catch is, okay, let's just say, so this would be 11 and this was 19 in terms of how long it took to get to a point. So obviously this one was moving almost, you could say, twice as fast. It certainly wasn't 14 or 15 or 16, to balance with the 19 and be 1.4. So it was going substantially fast. Okay, but that's the argument, right? So he was doing it on glass, which probably means friction wasn't that big a deal, but this did rotate a tiny bit more. And you could argue that, as I argue, that friction is harder on the heavier object. The heavier object loses its energy to friction faster than the lighter object moving faster. So a light object moving faster loses less to friction per inch. So the longer you test over the distance, the more of a bias there is, because this will lose its energy much quicker than this will. So you could say, yeah, that maybe these real numbers should have been 12 and this should have been 18, and we're getting closer now. But regardless, the point is you have more kinetic energy than you should, and the indication is that you can make even more. And so if Brozo would have put this a little bit further out, okay, I would argue he would have gotten even more dramatic numbers. And that's the argument, is that you have to compensate for the differential in the fractions. Now his fractions here might have just been something like, you could say 11 fifths, and some kind of weird number. And this one was 13 fifths was the combined weight of the lever, and how much the lever was absorbing of the total mass. But anyway, just depends on how much the lever weighs. Can't emphasize that enough. The weight of the lever matters. And I sort of, just put another experiment into context. So we have this experiment that's pretty decisive. Frankly, it's a pretty strong piece of evidence that the 1.4 thing ain't happening. Kinetic energy isn't being conserved, and that actually momentum is, if you include the lever and the mass. All right. I was going to say something, and that's gone for a minute. Well, I guess I'll just say that we have things as context, previous experiments. So I could argue the Mythbusters experiment is also indicating that momentum is being conserved, not kinetic energy. So there are other experiments that counter Ian Gosling's projection. And again, it's the projection in light of the fact that he has had to make improvements to his experiment. And in making those improvements, he is getting more of a differential. And I would argue that the more he improves the experiment, the more it'll come out consistent with conservation of momentum. Now, all of that can be calculated if we could get better images of the actual distance they're traveling, and more importantly, if we get some good height data. So the more precise that gets, because you can do the simple experiment of put both objects on the lever, and it will use the same momentum. Okay, it will conserve the momentum, and then put one object on and then put the other object on, because all those three experiments will all use the same force, and it'll all be revealed in the outcome. So if you take the momentum of the object launched and the momentum of the lever combined, it's always going to be the same momentum. All right, so I guess that's enough of a context. I don't know, I've already said this like 3 times, talked about the weight of the lever. It was a surprise that it is how much it matters, and now it has to be dealt with, and he wants to pretend none of that's been learned. Alright, so I guess we'll play the video. I haven't played it yet. I did read some of the comments, and clearly people are just not on the subject. So my whole point in saying, well, when are you going to concede? He's already getting more kinetic energy, I would argue. That seems apparent. So he's getting more kinetic energy than he should. Indicating, okay, that, again, if he knows, I think, from his own previous experiments, that if he just moves the lighter object over, he's going to get more and more and more velocity out of that object. That momentum can't come from nowhere. Their momentum is either in the lever or it's in the object being thrown. There's only 2 places for it to be, is the argument. So unless you're going to explain a third place the momentum could be, go ahead. But clearly, all you got to do is make an adjustment for those uneven fractions, and the experiment's going to start going south on you, in the sense that it's going to get 1.6 and 1.7, 1.8, 1.9, and 2.0 if you finally get those distances right. Alright, so I think that's enough. Yeah. Yeah, there was one where he linked to a dispar analysis that cheated the argument right from the start, because it counted the forward push of the little, he puts a little, which was a great idea, frankly, a little stick on here to make it even, because the arcs of the 2 objects aren't going to be the same when you launch them. So it fixes that problem. But what it does is lift it a little bit, because it's pushing it forward, so it lifts it a little bit. And Dispar took the wrong measurement, and so he said this thing was much higher than it actually is by comparison, because he started off with subtracting a ½ inch, or whatever you want to call it, by this perception. I already showed the image of the object flying right off the screen. So again, instead of just redoing the experiment and try to get better and better results, especially I pointed out the inconsistency part, where he gets a 20% range in the reading for each test, which is pretty bad. So, fixing that kind of stuff would probably be more important than trying to reclimate a previous experiment by tying things. But whatever. This is just there's no conversation. I don't think this is a rational thing to do. The images speak for themselves, so to speak, can be understood for themselves. I don't need you to take the image and give me your stringed interpretation of it. I can have my own stringed interpretation. I mean, what's the point of it? You haven't done anything. You haven't added any real value here. You've just tied things where you think they were. And where you think they were is dependent on how you interpreted the photographic images. It's really bullshit.
Oh dear, Gary. It looks like I've got to correct you again. You remember?
So all this unnecessary bullshit, okay? The fact is you haven't corrected anything. You're not going to correct anything. You're not going to deal with the argument that was made 3 times. I mean, 3 times I spelled out this truth, okay, that, it's not the same experiment. The energy can't get lost. The force of the spring has to go into the lever, and it has to go into the objects. There's no place you can put the object where the energy doesn't go anywhere. So that's why no matter where I put the mass, it still goes with a substantial velocity. It just doesn't matter, okay? Because all you're really doing is taking away how much energy the lever uses. 3 times I went over it.
The other day you got something. You was all over the moon. You thought it proved you got.
None of that happened. I just said, look, you created more energy. Okay, this experiment came out with the objects being separated by a lot more distance. Just no doubt about it. So the little stick improvement is the hitter, the different cutting the edge off the lever. These things did change the experiment, and the changes aren't good for your side. And that's just a fact. And if you just move the object further out, you'll see the outcome.
4 times the height when I first did this thing. And we had to point out that, or I had to point out that you were way up.
Alright, so there's just no point, right? This guy just keeps ignoring context. So I'll say again, he's a pathetic, lying scumbag. He can't be trusted at all, because he has never explained why, when he did the clay experiments, those were worth hiding. So he didn't show us any video of when he dropped objects on the clay, the 2 mass versus the 1 mass, 4 times the distance, the whole same ratio thing. And he got the perfect outcome, which was saying, yes, they both have the same momentum. They both crushed the clay the same amount. He hid that experiment, and his excuse was somehow the clay is faulty. Even though the results were perfectly consistent each time, the clay was faulty.
Over, got that all wrong. To eat a bit of humble pie, although you never.
Some more of this bullshit. You measured an experiment wrong. Is the video still up? I mean, do I really have to go look and see if you still have the video up where you say it's a proof? The title of your video is proof, and you didn't even calculate the frickin' height correctly. You got 4 wrong. 1 and 4. You couldn't handle 1 and 4. That was above your pay grade. So you really are just so obnoxiously duplicitous, hypocritical, and duplicitous.
Said anything, you just made excuses. Well, you've really done it again this time, haven't you?
No, I haven't done anything. I predicted the outcome, and I'm predicting the outcome. And again, I'm just look. It was my bad for thinking you would recognize that. Oh yeah, this is past twice as high. That's not good. Okay, and all I have to do is move this thing out a little bit further, or I move the other mass in a little bit further, and it's going to be a lot more than twice.
This is proof against our 1.4, you're saying? It's way over 2. Way over 2. And you can't. I've set this up again, taken the trouble to try.
No. It's not taking the trouble. I pointed out in the last video. This is just you playing games. All right. Where did you get the precise information from? Anything other than the same images I saw? There's no difference. You're just saying, I'm going to decide to tie it here, and I'm going to decide to tie it here. You know, fuck you and that bullshit. The fact is it flew off the screen. That's the fact. The fact is it flew off the camera's viewing perspective. And you're just approximating where that was. How nice of you.
Try and reproduce the screenshot on your video, your latest video. To be fair to both the weights, the half mass in its highest position.
So it was a really shitty experiment, all right? It takes 60 seconds. He just slops through it. He's dancing and singing while he's doing the experiment. 30 seconds worth of work to do the actual experiment carefully. He's flipping it, making jokes about flipping, and you can see that every flip is a different height. Every single one. And he doesn't see, oh, well, maybe I should fix that. Maybe I should take this a little more seriously and try to wait for everything to settle and do everything precise as I can to try to be a little more consistent. He doesn't even figure that part out. So he has a shitty video. The objects fly off of it, plus there's all kinds of variation. You could pick a number where this was at this black line. I could pick one where it's at the white line. Same with the higher mass. So it's just bullshit.
And the one mass about as high as it got. Centre of mass in line with the second line up. And the half mass is just over.
The point is, compared to your previous experiments, there was at least a 20% difference here. Okay, this was a substantially wider gap between the two. That was the point. So you're finding out that, yeah, these little details matter. Cutting off the end of the lever, creating a better contact point. These things mattered that you weren't paying much attention to. And the fact is your experiment is now improving. And my argument is I can't say it more than 15 times, right? How many times do I actually have to make the video where I tell you you actually have to account for the fact that you do not have an ideal lever? You in fact have a very less than ideal lever, and that you have to compensate for that by pushing the masses further out.
The top line, just over twice the distance, twice the height.
Yeah, just over what you don't want as an outcome.
Which is a little bit more than 1.4.
Yeah, right. You can expect the experiment to lose energy. You don't expect it to gain energy.
Way short of 2 times the speed, 4 times the...
Right. Well, that wasn't my argument, okay, that it showed 4 times the height and all that crap. My argument is that it's going much faster. That was my argument. But whatever. It's okay. I didn't make any declarations. I just said, let's see what they say. Let's see if what they say to the fact that even without moving it further out, they've got more kinetic energy than they should have. So it's just an indication that really you're going to be in big trouble when you do what you're obligated to do, frankly. It's just a science fact that you have to correct for the different percentages of the energy being used by the lever. You have to compensate for that.
Right. How can you get away with it? Well, you're not going to get away with it.
No, I told you you're not going to get away with it, okay? Again, the experiments have been done. Brozo's experiment, for example, mine, okay, which I didn't say is good enough. All right, it's good enough to convince me, all right, but yes, I'll do it more precisely. I said that. So if I have to do the experiment correctly, then I will, all right, if you won't. And it's clear that you don't have any intention of doing exactly what I suggested, right? Well, you did cut off the end. I did suggest that. But otherwise, you're not trying very hard. I mean, I suggested it'd be nice if somebody just itemized. You know, just start with the item really close, then move it an inch, move it 2 inches, move it 3 inches, and see what happens. You won't even bother doing that.
People watching the video, your video, will see. So you need to concede, Gary. You need to concede that you're wrong here.
Yeah, well, I'm not.
You do. To have any credibility, of course. I mean, even your own supporters, when they analyse this, can see that you're wrong.
Whatever. Again.
Very wrong.
So again, I'm not very wrong. I'm very right. You haven't paid any attention to the argument I made 3 times. So you're pretending this is an ideal lever. This hunk of wood is an ideal lever. That's your argument. We can be treated as an ideal lever.
Oh, it's way over. If this is one height, which the one mass is getting up to, this is 2 times the height, which the half mass has just gone a bit over.
Yeah, one of them's under and one of them's over. That's basically saying you have too much.
To get your 2 times the velocity, we've got to go 4 times the height. So that's 3, and that's 4. It's up here with the top of the board.
Well, if you go by distance, okay, go by the distance, and it's almost, like I said, it's close enough in some respects. All I have to do is increase this distance to be the same as this distance. Okay, so it's halfway, more than halfway there. But whatever. Just point made, okay. You know, I like I said, I'll have to wait and see what he says. This is your reaction. So your reaction is you're not going to bother doing the experiment I said you really have to do, which is you have to put the lighter mass further out so the lever takes less percentage of its energy. And you just won't do that.
Miles off of what we've got. Consistently. There's a little bit of variation, yeah. We're getting 2.
It's off the screen. Yeah, a little variation. It flew off the screen.
2 to 1 wherever we put the weights. Wherever we put the weights in whatever configuration.
Okay, so he's lying again. I point, you know, we already saw that's not what happens. The further out you put it, the further it goes. So he keeps saying it's the same. No, it isn't the same. Because all the lever knows is it's pushing a total mass in both cases. And if you put them both in the same location, the fact is that you're going to get these kind of results because of your 1/3 versus 1/5 relationship. A lot more energy is stolen from the lighter object and goes into the lever. Fact.
Now the point here is you've got to concede you're wrong, and you've got it wrong. Whether you want to apologise or not, it's up to you. But at least you could say, yeah.
It's just unwatchable nonsense. Again, so I don't have to apologize. Again, I can just go with the Brozo experiment forever. I could just argue, what are you going to say, he cheated? What did he do wrong? Why don't you explain how that experiment came out completely different than what you say I have to accept? And like again, we could, as imperfect as it is, I go back to Mythbusters, I could go back to car crashing, and then ultimately I could just go back to the day you show me it taking twice the fuel to go, 4 times the fuel to go twice as fast, or 25 times the fuel to go 5 times as fast, then I'll concede. But till then, you're out of luck. Your theory doesn't work. It mechanically doesn't happen. Those things don't happen. I think you know they don't happen, and I think you know you can't tell me why they don't happen. You can make a relativity argument, but it's not going to make any sense, is it? When I'm going 20 miles an hour, somehow my gasoline has twice the octane? Yeah, no, I don't think so. As when I'm going 10? That would be absolute bullshit. I mean, only a moron could believe that.
Okay, I got that wrong. That's just over 2 to 1. The long way short of 2 times the velocity.
Right, and I explain why it's a long way short is because 1/3 and 1/5 are almost 2 to 1. Okay, so you're getting close to having a prejudice against the lighter object that's almost as significant as what you're trying to find. So it almost explains the entire discrepancy. And the fact that you're getting a little bit extra here indicates that that's the discrepancy. If we could actually make the lever a little heavier, then you could actually get to a discrepancy in those fractions that would be exactly half. So one would be 2/3 and 2/4, and one would be 4/4 of the. Well, it can't be 4/4 of the energy. But anyway, you'd get a fraction that was actually twice the other fraction. I mean, 1/6, right, would be there. That would be the way to go, right? 1/6 would be half of 2/3.
Long way short.
No. 1/3. Yeah, well, anyway.
And also, the parallax error here is
So he doesn't even know what parallax error is. The further away an object is what's getting parallaxed. The closer object looks higher, and the further the object is away, it ends up looking lower. So he doesn't even know the parallax error is against me. It's not for, it's not against you. The parallax error is making the closer object look higher, and it's making the further object look lower. So you haven't even gotten that correct.
Favoring the higher weight. It makes the higher weight look higher.
That's a stupid, ignorant statement. You're wrong. Because you're below the objects, that's not true, stupid. Yeah. Below the objects, parallax makes the closer object look higher. It makes the further object look lower.
More than it makes the lower weight look higher.
Wrong.
I can see it by looking along the camera's view as I move up and down. The higher weight,
right.
as I go down, the higher weight gets disparate.
This is a guy who says he can see it when he hasn't gotten the camera angle right in a single video. Yeah, but he can see it.
Fortunately, higher than the lower weight gets higher. So there's a little bit of that. If we take all these things into consideration, it's roughly 2-to-1.
Okay, so he didn't take anything I said into consideration. So he thinks he has an ideal lever, and the ideal math applies. So it's a weightless, infinitely strong lever. And he doesn't have to account for the energy the lever's absorbing at all. Okay, that's his argument. It's a really dumb argument, frankly.
A long way off, you're a long way off. Not us, not science, not physics. So come on, you're not going to...
Again, why do you think I should have some doubt, exactly, about momentum being conserved? I guess, like I said, you can't explain how this kinetic energy thing ever happens anywhere. Again, I could go back to the 10-ton train, 5-ton train. Do you actually think if I had a tug of war between a 5-ton train going 10 miles an hour and a 10-ton train going 5 miles an hour, that the 5-ton train would decisively win? Do you really think so? I mean, are you that fucking stupid? Shit. They have the same energy. I mean, how can you think any other way? And again, the whole example of dropping the weight. I mean, these are classic videos. You just add the extra weight, and somehow you lost half your kinetic energy. And you have this insane excuse that you bent things and broke things and all kinds of things flew off because half the energy was lost. That's a lot of energy. If we had real 5-ton train, could you imagine half the energy of a 5-ton train going 10 miles an hour? How much damage that would actually do? That's a tremendous amount of energy you're losing, and you lose it every single time. No matter how gracefully you combine the two masses, you always lose half the energy at least. You can lose more, but you always have to lose half. You can't understand how that makes zero sense. Then I pity you. You're so... Well, I mean, there's no point. I mean, you just demonstrated you're an asshole because you don't even get the parallax thing right, and then you make a statement about it.
get away with it. You've got to concede that you're wrong.
Yeah. Pathetic. You've got to concede that you have no credible evidence on your side. Okay? Because you don't. Amazing. Alright, so I don't know if that's worth bothering. The comments are just all over the place, so I don't think there's anybody saying anything that matters. Brozo talking about 2 cameras. Well, that isn't a very long one, so that's better. So he is saying what kind of complications you get into. Yeah, that's the whole problem, is recognizing that none of these experiments are as simple as you would all like them to be, and that you can just do them in your kitchen. Okay, you got to be kind of careful about all of this. So we'll just leave it there. Yeah, like I said, the Dispar analyst video. Okay, now he's conceding it's 2.2. So at least he's conceding it's a little bit more energy. But I mean, he cheated in kind of an egregious. I mean, I should go back to the image and then you can see. So there was nothing in this video but this rant of his. So we got no information. He still hasn't really weighed the lever. We really don't, I mean, he really should have these. I guess the masses might be in the first video he did. So I'm not sure if they're exactly half. So that I should also check. Because all of this is going to matter. Well, it really wouldn't matter if he'd just do the experiment as I described it. If he would do the fix it by doing what you need to do, which is allow the lighter mass to have its fair share of the energy. And once you give it its fair share, okay, it will demonstrate the truth. But you won't let that happen. You want to cheat the poor little half mass. Alright, so, yeah, I'll pause. I don't really think there's anything worth saying more. Alright, so, closing remarks. I think Ian will concede, even without doing the experiment. Now, if he moves the lighter mass an inch further out, he's going to get even more velocity into the lighter object, and it's going to go much further. And that there is a point where it's going to go twice as far or 4 times higher. And he's going to claim, I guess, that somehow that's cheating the experiment. Now, I'll argue that no, that's fixing the experiment, because frankly you can never change how much momentum goes into the lever or the object. There's no way to cheat it. Okay, the spring will put it in. If I have just the lever with no masses on it, the lever's going to move really fast. And so whatever mass I put on the lever, it's going to absorb whatever energy slows that lever down. And that's the fact. That's how it's going to turn out. So if you add up the momentum of the objects and the lever, it's always going to be the same. So the velocity of the object combined with the velocity of the mass of the lever is always going to equal the same mv. It's always going to be the same total mv. And I don't think you'll ever prove otherwise. Okay, you'll never destroy the momentum. And again, you have to destroy momentum to conserve kinetic energy. So in all these experiments, there is no choice. In the 5-ton train, 10-ton train example, it's clear. If you conserve the momentum, you have to destroy the kinetic energy. And if you conserve the kinetic energy, you would have had to destroy momentum. Either create free momentum or destroy momentum. So in all of these examples, I mean, even if they could just acknowledge one sentence I said or one argument I make, if they could just acknowledge that it's always true that if I take energy from one object that weighs a certain mass and I now put the same energy that was in there in some other object that weighs more or weighs less, that it is impossible to conserve both kinetic energy and momentum. They should at least be able to concede that one point, that this argument isn't about you're going to prove that somehow the theory there's just a semantics difference between momentum and kinetic energy is just absolute nonsense. They're completely different theories of how reality works. Completely different. And it's illustrated when you exchange energy between different objects. Alright. But whatever. Till next time and such. Like I said, we'll see if he does what I said to do. Okay, if you want to find out the truth, then that's what you do, and then you can explain it. So move the lighter mass more, further away, okay, more than twice the distance, and see the results. And if you get what I predict, that is, there'll be a point where you will actually create the 2-to-1 relationship, or the 4-to-1 in height. Then you can explain why somehow it's a cheat. And then maybe while you're at it, you can explain how clay cracking somehow makes, experiments completely fail with the same consistent results each time. Yeah. He's such a weasel. Anyway, till the next time, such.